Now we will talk about model reference control systems. We will talk about the application of this approach, model reference approach, to control system design. We have two issues. The first issue is building a linear model following system. And the second issue is building the adaptive model following system. Both issues, they actually are two stages of the model reference design. And we will start from the first stage, the linear model following system design. What this linear model following system is about? Effectively, it is building a second control loop that would force output of an existing negative feedback system to follow a special reference model. It means that first we have a control plant, then we build the controller to stabilize this control plant, and at this point we're looking basically concerned about the stability of the system with the control plant. And only at the second stage of this design we introduce the reference model. A reference model is consistent with the design specifications, and then we design additional circuitry that would enable or force our designed system to follow the reference model. You know, linear model following design requires to utilize properties of the controlled plant, properties of the existing system. It is inconsistent with the very concept of adaptive control. In adaptive control, we are supposed to minimize the usage of the information about the control plant. Well, linear model following design would fail if properties of the control plant are not completely known. But, as I said, linear model following design later could be converted into adaptive model following design. We will start, as I said, from the linear model following design. Let me show you the system configuration. I want you to recognize a controlled plant and its feedback controller. And then you see the reference model that represents desired closed-loop dynamics of the system. And then we add matrix Km and matrix Ku. And if matrix Kp, matrix Km, and matrix Ku are properly defined, the properties of the system will be exactly the same as properties of this reference model. Later, we should be able to introduce different reference model, change matrix Km and Ku, and guess what? The system will follow this new reference model. I was told, I'm not sure whether it is an anecdote or it's a real situation, that it is possible, and it was done more than once, to introduce a reference model that represents dynamics of B52 and create a linear model following system that would force light aircraft to have the same dynamics as B52. And of course, this application seems to be very well justified for training purposes, one way or another. The matrix Km, matrix Ku, and matrix Kp could be designed only if we know properties of the controlled plant. Now, in the linear model following system, we can compare state of the reference model with the state of the controlled plant with its feedback, of course, extract the error. But when linear model following design is successful, this error is always zero, and there is no need to use this error for any purpose. Now, if there would be a error in the system design, then this error surely will not be equal to zero, and it would be possible to utilize this error for building a adaptation mechanism, but we will talk about this later. Right now, linear model following design is selection of matrix Km and Ku, this one and this one, after the control plant was stabilized by this controller represented by matrix Kp. You know, our design is intended for linear system. And after the linear model following system is designed, it is linear. It is called linear model following system. And therefore, the stability issue is not as pronounced as we would have stability issue for a nonlinear system. With linear systems, everything is simple. If system is stable, it is globally asymptotically stable. Let's consider the linear model following design procedure. We have the reference model that represents the closed loop system dynamics. The signal UM supposed to be external signal. It's not the control effort. It is rather a reference signal. It's a state equation. AM is the fundamental matrix of the reference model. And of course, reference model in this case is a simulator with fixed parameters, because we built reference model based on the design specifications. The next is the controlled plant. It has state vector y. AP is the fundamental matrix of the control plant. BP is the matrix of the control plant through which control efforts affect individual state variables. UP is the control effort, or input signal of the control plant. I want you to take a look at the controller. The controller generates UP vector. It has negative state variable feedback. It has contribution from the reference model, because X is the state vector of the reference model. And it also has the effect of the reference applied to the system. And the reference acts through filter or matrix Ku. This is expression for the error, but we do not use this error for any practical purposes. Error is used for mathematical derivations only. This is derivative of the error. This is the derivative of the error. But then this signal UP or vector UP is replaced by this expression. It is replaced by this expression. And then what we do a simple algebraic trick. We're adding this term and we're subtracting this term from this expression. We've done this before. As a result of these algebraic transformations, we're getting slightly different expression for the derivative of the error. This one. And finally, Look, AM minus BPKM with X and AM minus BPKM with Y. If we would factor out AM minus BPKM, then I will have X minus Y and it will be error. So this is the final working expression for the derivative of the error. What do we want to accomplish? We want derivative of the error to follow this equation. What this equation tells you? This equation tells you that error is supposed to converge to 0, and it will converge to 0, providing that this matrix AM minus BPKM would have appropriate eigenvalues. This equation is equation without forcing function in it. And for any stable system, state vector or vector describing this used in this equation supposed to converge to 0. Now, of course, it will happen if this matrix will have eigenvalues in the left-hand side of the complex plane. If eigenvalues are complex, then this convergence process will show some oscillations. If all eigenvalues are real, then the error conversion process will be purely exponential process. So this is how it works with this type of equations without forcing function. You know, the terminology that is used is this: AM minus BPKM must be a Hurwitz matrix. Well, all its eigenvalues should be in the left-hand side of the complex plane, which means this is the definition of the Hurwitz matrix. How to create this equation, how to achieve this condition? Take a look at the previous result. This is expression for the error. Well, I guess if this part of the equation is 0, and if eigenvalues of AM minus BPKM are properly chosen, the error, the difference between the reference model and the control system, will be approaching 0. And this is what we want to happen. So, we have to make sure that these two equalities will be assured. If these equalities will be assured, then what will be left from the derivative of the error will be just this part. Now, how to achieve these equalities? Well, AM is known, BP is known, AP is known, BP is known, KP is the feedback controller that we will introduce to stabilize the controlled plant. Km should be found from this expression. Should be found from this expression. Now, BM is known, BP is known, KU is the matrix that should be determined from this equation. And this is what basically we do. BPKM should be equal to this sum of 3 terms, and BM should be equal to BPKU. How to get the solution? Look, it's not that simple because we're dealing with matrices here. To get solution, first of all, we have to make sure that we have matrix Kp. To get matrix Kp, what we have to do is to apply the pole placement procedure to obtain the state variable feedback controller with matrix Kp. If we would properly choose Kp, we would achieve requirement that AP minus BP Kp is a Hurwitz matrix or has all left-hand side eigenvalues. So this is effectively the problem of stabilizing the control plant, making sure that control plant has appropriate settling time and overshoot and things of this nature. Or at least control plant with this state variable feedback must be stable. This is the most important issue. When matrix Kp is defined, and solution for matrix Kp is not different from solution for control system design in state variable control. When Kp is defined, we have to solve this equation. And we will solve it for matrix Km. How to find matrix Km? It's very clear, it's very easy to write that BP times Km is equal to this. And then we can say that Km is equal to BP in the power of minus 1 times this result, this sum. But you know what? Matrix BP not necessarily is a square matrix. It helps when it is a square matrix. What if it is not a square matrix? In this case, the pseudo-inverse should be used. How to use pseudo-inverse? We will multiply left-hand side of this equation and right-hand side of this equation by this term. It is BP transpose times BP inverted times BP transpose. This is what we will get. If this is done, then please note that in the left-hand side, BP transpose times BP in the power of minus 1 times BP transpose times BP should be unity. So in the left-hand side, we will automatically get Km. In the right-hand side, we will have BP transpose times BP in the power of minus 1 times BP transpose times AM minus AP plus BP Kp. You know, this expression is known as the left pseudo-inverse of non-square matrix. Obviously, this left pseudo-inverse exists only if BP transpose times BP is not a singular matrix. Well, after Km is defined, we have to define matrix Ku. And if necessary, if matrix BP is not square, we will be using pseudo-inverse again. We'll be using the pseudo-inverse again to define matrix Ku. You know, fortunately, there are not that many practical cases when pseudo-inverse is required. So you don't have to get too much involved, you don't have to think too much about the use of pseudo-inverse. Just keep in mind that this operation exists and could be utilized. However, it could be a slightly different way to solve the problem. You know, AM minus BP Km is equal to AP minus BP Kp. But AP minus BP Kp is nothing but a fundamental matrix of the closed loop system. So later we should be able to work not with AP, BPKP, and AM, but we should be able to use this expression. BPKM is equal to AM minus A closed loop, and then KM would be equal to BP inverted times AM minus A closed loop if BP is a square matrix. And this is what we will have if matrix BP is not a square matrix. This is everything what I am supposed to tell you. It's not very mathematical, this part of the system design, and what you have to do is to use it. And let's use it. I have two examples prepared for you. The first example is the control plant with state vector Y, and matrix AP is the fundamental matrix of the control plant, and this is matrix BP, and U is the control effort. Very easy. This is definition of matrix AP, this is definition of matrix BP, and this is definition of matrix C that may be used to define the output of the control plant. If you would take a look at this matrix AP, you would realize that its eigenvalues not necessarily all in the left-hand side of the complex plane. As a matter of fact, this control plant with this matrix AP is unstable. We don't want it to be unstable. We want to stabilize this control plant. And therefore, we will make sure that the closed loop system will have these eigenvalues. The stabilized control plant will have this the fundamental matrix of the stabilized control plant will have these eigenvalues. Well, what we do next? The next we will, based on this eigenvalues, come up with the characteristic polynomial, desired characteristic polynomial of the closed loop system. And then, based on this characteristic polynomial, since we know the canonical controllable form definition, this is the closed loop fundamental matrix of the closed loop system for the stabilized system, for the system with the matrix Kp in the feedback. Should look like this. Should look like this. Because this is the fundamental matrix that has the required eigenvalues. If this is the case, you know from our 462, 510 material how to define matrix Kp. We have AP minus A closed loop. It's a square matrix. They both are consistent with the canonical controllable form. If you will cut out the last row of this difference, this is what you will get. And this is the matrix Kp. So, the control plant was unstable and we stabilized it. Period. But now it's time to recall the design specs for our system. And these design specs should be incorporated into the reference model. And this is the reference model. So, in this reference model, I don't have a way of telling you what eigenvalues are, but it's surely a system with all eigenvalues in the left-hand side of the complex plane. It's a stable system, and so on and so forth. Our goal now is to define matrix Km. Look, BPKM is equal to AM minus AP plus BPKP, but KP already is there. So minus AP plus BPKP is a closed loop. A closed loop. So what we have is this. This is matrix BP. This is matrix Km. And it should be equal to AM minus a closed loop. And from this expression, if you would carefully look through the matrix transformations that are very straightforward, you will find out that matrix Km is equal to this expression. This is the matrix Km that we have to have. The next what you will do, you should recall the second equation that we have to satisfy, and since BP is 0, 0, 1 and BM is 0, 0, 1, matrix Ku should be equal to 1. Our design is accomplished. Well, I guess it's a good exercise that could be offered during the test to students. Finally, the key issue is to show the control law for our system. Look at the control law. This control law is Ku times the reference, whatever the reference signal is, minus Kp times the state vector of the control plant, plus Km times state vector of the reference model. And this is the same expression. And the same expression in with all matrices defined numerically. Ku is 1, so I have reference. This is the Kp times y state vector. This is Km times state vector of the reference model. The control law is the final result that we're supposed to have in order to implement the system. I want to offer you a much more challenging problem. It will be design of a multi-input, multi-output decoupled system using the linear model following design approach. First of all, take a look at the state variable description of a 2-input, 2-output controlled process. This is state vector of the controlled process, the fundamental matrix of the control plant, state vector, matrix B of the control plant, and input control effort U, and this is the output vector of the control plant. It's important to show you the numerical definition of these matrices. Look, this is a fourth order system. This is matrix AP. This is matrix BP, which tells you that we need four control efforts in this system, for this control plant. 4 control efforts we need. And this is matrix C, that shows that we have two outputs in our controlled plant. The situation is not that simple. And if I would take eigenvalues of matrix AP, here they are, 4 of them. The right-hand side at eigenvalue, a left-hand side at eigenvalue, and right-hand side at eigenvalue. So this control plant is surely unstable. But it's even worse. By looking at the fully populated matrix AP and fully populated matrix BP, one should conclude that the system is not only unstable, it is also cross-coupled, which means that each control effort affects all outputs of the system. It's a cross-coupled system. First of all, we would like to stabilize the control plant by making sure that the stabilized system will have this fundamental matrix with eigenvalues -1, -5, -6, and -10. These values are arbitrary, but the task is very particular task with stabilizing this unstable control plant. It's just a matter of doing system design. Look, this is the closed loop, the fundamental matrix of the closed loop system. AP minus BP KP is equal to a closed loop. And because of this, I can easily determine matrix KP like this. Like this. Now, matrix BP is a 4 by 4 matrix. It has to be inverted. Matrix AP and matrix A closed loop are 4 by 4 matrices. So, from the computational point of view, it's a quite elaborate task. Therefore, it was done using a computer. And this is the matrix KP defined by the computer tool. And I printed it out. You want to take a look at the fundamental matrix of the resultant closed loop system? Let's take a look. Let's verify our result. Yeah, this matrix is AP minus BPKP. And you understand it's a 0, this is 0, this is 0. I have 1, 0, 0, 0, 1, 0. You know, effectively, this is the same matrix that initially was presented as a closed loop. The goal is accomplished. The fundamental matrix of the system with controller KP is exactly the same as a closed loop. System is stable now, but it is still cross-coupled. Now we can consider the reference model. And this reference model is supposed to represent the desired system properties. For the reference model, state vector is X. This is the fundamental matrix. State vector X, matrix BM. R is the reference signal. This is the output of the reference model. And here are definitions of matrices. Look at the matrix AM. It has block 1 and block 2. State variables are fully isolated from each other. Look, this is block 1 and this is block 2. This system, this definition of matrix AM and matrix BM surely represents a decoupled system. surely represents a decoupled system. You know, these numbers -4, -5, and -6, -7 probably refer to the desired overshoot and settling time, and I don't worry about this part. My problem is to build a system that would be a decoupled system. You also should realize that our model represents a two-input, two-output system with two decoupled second-order dynamic channels. And it's our goal to build such a system using the linear model following approach. First of all, we will define matrix Km and Ku because we have to, and we do it by solving these equations. These equations are consistent with the linear model following design. This is solution. Since matrix BP is a square matrix, we can define Km using the inverse of BP. And we define matrix Ku based on the fact that matrix BP is square and we can invert it. Now let me show you Km and Ku defined by numbers. This is matrix Km. I got this result from a computer tool. And this is matrix Ku. I have this result from a computer tool. And now it's time to talk about the control law that incorporates components of the linear model following system. Control law is this. The control effort applied to the control plant is equal to matrix Ku times the reference vector minus state variable feedback, it is Kp times y, and plus matrix Km multiplied by state vector of the reference model. It is anticipated that with this definition of the control effort, with this control law, our system will behave as two independent systems. In other words, our system will be decoupled. Again, the control law is defined, but we have to go further. We cannot stop at the point when the last formula is written. We have to make sure that we know how to implement the system, and we will implement it in the simulation domain. First of all, this is the control plant. The control plant has 4 state variables, 4 control efforts, 4 state variables, 4 control efforts. This is how we get x1. This is how we get, this is how we get y1. This is how we get y2. This is how we get y3. And this is how we get y4. Now, if you recall matrix C for the control plant, it expects that we will have 2 outputs in this control plant. And these 2 outputs are W plant 1 and W plant 2. This definition of outputs is consistent with this matrix CP. The control plant is there. Let me show you the state variable feedback, which is minus Kp times state vector of the control plant. This is the state variable feedback. And believe me, I typed in every single element of the matrix Kp that was determined using or calculated using the computer tool. I want you to keep in mind that I introduced special variables v1, v2, v3, and v4 that will be used later in the control law. The next what we will do, we will consider block Km times x. And again, this control block represents the product of matrix Km and state vector x of the reference model. And I guess it's all done properly. All these coefficients, all these numbers are typed in from the computer printout. And I introduced variables h1, h2, h3, and h4 that I will use later in the control law. The next what is done is the reference model. The reference model has 4 state variables. It has 2 reference signals, and all these elements consistent with the elements of the matrix A and matrix B of the reference model. And here are the state variables of the reference model, and the reference model also has 2 outputs, WM1 and WM2. Now it is time to introduce the controller. Look at the controller. Controller has 2 input reference signals. Each of these reference signals is multiplied by the appropriate element of the matrix Ku. So these 2 elements constitute the first row of the matrix Ku. And then I am adding the variable h1 and variable v1 that represent the appropriate components of the state variable feedback and appropriate components of the reference of the matrix Km multiplied by the state vector of the reference model. This is the control law. The next what we will do, we will show you the overall system operation. Look, I have the controlled process with 2 outputs. I have the state variable feedback mechanism, which is represented by minus Kp times y. I have this block that connects our system to the reference model. It has Km times x. This is the reference model itself, and this is the control law. If you remember, control law had 2 inputs, R1 and R2. Right now, I'm applying step to the input R1. And I want you to see very clearly that the first output of the controlled plant shows nice, properly controlled transient process. And the second output is effectively equal to 0. It should be exactly equal to 0. However, when I was typing in the numbers, I did some truncation. Now, exactly the same situation. However, the input step is applied to the input number 2 of the controller. And situation is reversed. You can see nice response in the output number 2 and response virtually equal to 0 in the output number 1. What I want to do now is to run the simulation. This is our simulator. Okay? This is our simulator. Look, this is the control plant as it was originally presented to you. This is all simulator, it's not a picture. Simulator. This is the state variable feedback mechanism. Exactly consistent with what I told you earlier. It's a simulator. This is block Km times X right now. You can see it. Consistent with my earlier discussion. This is the reference model. And this is the control law. Now, let me apply input signal, input step, to the reference input number 1. System, go. And you see exactly the same picture that was originally shown to you. Now I will excite input number 2. System, and go. What is happening here? You know, it is just a matter of scaling. The response of the output number 1 is not exactly 0, and because of this, our simulator did this experience some scaling difficulties. It shouldn't go up to -1 and shouldn't go up to 2 in this drawing, but look, this is what the simulator does, and this is beyond our control. I would say that this numerical example shows you the main issues in model reference design. First of all, you have to stabilize the control plant. And when you stabilize the control plant, your only goal is to achieve the stability. The specific eigenvalues of the closed-loop fundamental matrix are not that important, but they should be in the left-hand side of the complex plane. The second stage is assuring the compliance with the design specs, and this is done through the reference model. So the reference model is formulated based on design specifications, and then we perform additional computations. We have to establish matrix Km and Ku, and finally the system should be assembled together, and the control law will have contribution of the reference, contribution of the state variable feedback, and contribution from the reference model. The last comment is this. Everything what was done here is based on the exact knowledge of the properties of the control plant. Linear model following design. This linear model following design would fail if we would not have the exact knowledge of parameters of the plant. Later, we will convert linear model following design to adaptive model following design. And basically, the purpose of linear model following design is to do the groundwork for adaptive model following design.